Okay, welcome to the lecture on phase transformations and phase development and structure development. What we're going to talk about today, let me make sure my pen is working. It seems like it should. What we're going to talk about today is how we develop structures and materials, and we're going to talk really about how chemistry leads to the phases that we have and talk a little bit about how cooling rate matters. And of course, there's a lot more we can do with that in real life. We're much more advanced. We worry about cooling rates deeply. We also work the material, put deformation into it to try to modify and refine the phases that way. All of these things are important. What we're going to do today is give you the absolute basics on top of that. Here's the big idea. Materials depends, first of all, quite a bit on chemistry. Chemistry leads to phases. We get structure that includes size, dislocations, grain boundaries, all kinds of stuff like that. Then processing plus materials chemistry leads to a microstructure. Again, the big idea, microstructure controls properties, and things like cooling rate, deformation matter. We're going to start with the basics first and give you something that you can teach, something that is very fundamental, something that works all over the place. So what we're really going to talk about is the phase diagram, and we're going to use something called the temperature composition phase diagram. This can show three major things. First of all, what phases exist at a temperature composition point, what the composition of each phase is, what the volume fraction of each phase is, and then we're going to show a little bit how that's connected to solidification structures, talk a little bit about how cooling rate can play a role, not much. So here's what we are interested in. In the end, we care about where the atoms sit, how that makes up the material. That's really what we care about in the end. If we look at this microstructure that we can look up, it's really blown up. This comes from some composition that sits at some temperature. If we look at the microstructure, what phases do we get? We covered this before. And the idea here, this is a solid solution. This is phase A. You can see these copper atoms, which are indicated by these guys, and the aluminum atoms indicated by this, are randomly mixed up. But then there's this other region here that's fairly ordered. Let me change my color just so I can kind of, this area here is ordered. You see these lines of atoms. That's a separate phase. How do we know it's a separate phase? Because it's physically distinct. Something different is going on with the way the atoms are lined up there. So components and phases, some fundamental definitions are as follows. First of all, components are the elements or compounds that are mixed. We're going to do some things with ice water in a little bit, where H2O, which isn't an element but a compound, they're mixed. Phases, we've mentioned before, physically and chemically distinct regions. And then compositions are the amount and components in a phase. So again, we can use this to talk about elements, compounds, solutions, mixtures, all those kinds of things that we typically do in liquid or gaseous state chemistry. So here's a real example. This is a real aluminum copper alloy. You see two phases here. You see a light structure, which we usually call, we give these things Greek letters. This is something we call beta, and then alpha is this darker phase. And we can surmise, we can't prove this just by this optical micrograph, but a lot of experience on this, that these are distinct phases, they have different properties, and they fit together to give us something that's special, unique, and useful. That's why we do it. So let's start with a simple example. This is an ice-salt phase diagram, mixture of two phases, and this is basically a map. Temperature's on one axis, weight percent sodium chloride is on the other. And with temperature, we know 0 degrees C is an important one. If we deal with pure water, above 0 degrees C it's water, below 0 degrees C it's pure H2O. But if we add sodium chloride, salt to that, we know that we can stabilize pure water or pure liquid. We can have liquid water stabilized, I should say, at a temperature of -10. If I go really cold, even if I put a lot of salt in it, it still turns into a solid. This is why if you have really cold climates, they rely on sand instead of salt. It doesn't work if it's really cold out in Fargo, North Dakota or something like that. But the most fundamental thing you see here is you got different regions here. This is ice over here, ice plus brine, all water, brine with another phase in it, water with sodium chloride with another phase in it. And that's the most simple way we can use this. It's a map where we've got composition, and temperature. It shows you what you're going to get. And the other really interesting thing is, and we know this if you've lived through a winter in a place like Ohio, is you can have these slushy regions that are persistent. It's an equilibrium that you have solid and liquid that just persist in equilibrium. They'll stay like that together. Is this two-phase region where one phase is the ice crystals, the other phase is the brine, the water, the salty water, and that can sit there in a salty, slushy puddle for weeks. And we know that's true. That's also the chemistry for things like a slushy. And that's basically that. So let's consider the effect of temperature and initial composition. C naught is our initial composition on phases. And let's change temperature as we go from path A to B. What you see is you're going from that slushy puddle, heat it back up, you go to all liquid. And you can also go that way to all liquid basically by increasing the amount of salt in it. Again, this is one of the fundamental pieces of a phase diagram. It's a map that shows you what phases you can expect based on chemistry and temperature. Okay? So the next thing we can do is deal with real metals. And so it'll consider phase equilibria for a very simple one where we might have a mixture of nickel and copper. And there's reasons we often like to do this. We make alloys, make it stronger than either of the parent materials. And nickel and copper both like to form face-centered cubic crystals. That has a certain symmetry associated with it. I think most of you have seen this. They both have similar electronegativity, and their atomic radii are not that different either. Old famous metallurgy, Hume Rothery, suggested that if things are similar, they will tend to form solid solutions, and they do. And we can show this on this phase diagram for the copper-nickel system. This is increasing fractions of copper going from one side to the other. This is temperature increasing over here. Again, we have a map. If it's very high temperature, it's all liquid. If you have lower temperature, it's all solid. And in between, we've got this two-phase region. And that's sort of it's sort of an interesting thing. It's this slushy zone where you've got metal, and you'd actually have in this a nickel-rich metal and a copper-rich liquid that end up fitting together. These things tend to phase segregate. The compositions are not uniform. So you've got two phases, a copper-rich phase and a nickel-rich phase, and you've got three phase fields. One down here is this all solid. Here it's the mixed phase field, and the third one up here is the all liquid phase field. And even with this, both components have complete solid solubility in one another. You can put as much liquid, you can put as much copper as you like into nickel, or you can put as much nickel as you like into copper. It's still a single face-centered cubic crystal, but you still get this interesting two-phase region in there. It's not as simple as a single component system. Okay, so let's go back and visit our three rules of phase diagrams. The first rule of phase diagrams, if we know the temperature and composition, we know the numbers and types of phases that are present. So let's consider a particular point here where we've got 35% nickel at 1250 degrees C, so sit about there, 1250, boom, you get a point right about there. And we know that there are two phases present there, liquid and alpha. Consider point A, and I think I've got things that I don't, that show where those, I thought I had things to show those points are, I don't. If you have point A, it's sitting here at 60% and 1100 degrees C, and that point here would be all solid. Okay, let's go to the second rule of phase diagrams. What's interesting about this is you've got two lines here. The top one here is called the liquidus, where you meet liquid. Bottom one is called the solidus, where it meets solid. And what's interesting, if you got a position inside here, this shows that the composition of the liquidus is in equilibrium with the composition of the solidus. So what this tells you is the higher melting material, nickel has a much higher melting point than copper, the higher melting material ends up having this composition in equilibrium with that liquid. So it kind of makes sense. The thing that really wants to be solid stays solid, and then the copper segregates outside of this. So let's consider we're at T sub A. We only have liquid. What's the composition of liquid? Well, that would be 35% nickel is the composition, of the nickel. And if we're at TD sub here, equilibrium is you've got solid only, and it's going to be 35% nickel. If I'm at T sub B, I've got this composition of liquid here that's about 30%, 31% nickel, and that's in equilibrium with a solid that's out here at about 42% nickel. So the solid is more nickel rich than the liquid, and that should make some sense. The higher melting point stuff, the stuff that really wants to be a solid, does this even in that slushy zone. And that's a persistent slushy zone, and there's some actually interesting things you can do with processing all of that, but we're not going to go through all of that. Third rule of phase diagrams is the following. If we know the temperature and composition, we can also know the amount of each phase, and it kind of comes to reason. You know you have so many atoms, you know that you're going to have the liquid will have a different composition than the solid. So by this, if you have different compositions, only so many of each atoms, then you can only have a certain fraction of each phase, and you can show that mathematically. The next slide does that. We're not going to spend any time on that. But basically, the thing here is the lever rule. I'm just going to do it very briefly. But this is the overall composition. If the overall composition is just about the same as the liquid composition, the overall composition should be all liquid. If the overall composition is near the solidus, it should be all solid. Turns out what you can do is, for example, the percent of liquid is equal to this length S divided by R plus S. So if S is the same as R plus S, meaning this point goes all the way over to here, then it's all liquid. If S is really small, meaning the overall composition point is down here, it's going to be mostly solid. So we can work that out in this thing called the lever rule, and basically it says the fraction of liquid is going to be basically the fraction of this length to the total, R plus S, and the fraction of the solid alpha is basically going to be this R divided by that whole length. It's equal to R over R plus S. Okay? So that should be fairly simple. I'm going through this fast. This is to give the highlights. If you really want more, you can do a little more reading. There's a proof of this. It's just basically simple algebra that I'm not going to go through. But what I am going to go through is a little bit of what happens if you take something and cool it now. What's kind of interesting, you start out with this liquid. Again, it's sitting here at 35% nickel, all liquid at that temperature. Cool down and hit this line. What's it called again? This line is called the liquidus. Come down to point B, and you just start forming solid. And again, overall, you've got 35% liquid, but that solid is going to have 46% nickel in the liquid. So these are going to be little nickel-rich particles that end up forming. Get here to the middle. You've got something that's in equilibrium also here, where you've got 43% nickel in the solid, and you've got about 32% nickel in the liquid, and it's mixed. And then at the very end here, you've got just a tiny bit of liquid left, and that liquid is very much concentrated in copper, because the copper wants to stay molten, and then the rest of it is 36% at equilibrium nickel, and that's what happens when you solidify. You go through these different equilibrium phases. Well, there's a little bit of a problem with this, in that once you have the copper and nickel in solution with each other, it's difficult for the copper to move around, or the nickel to move around, so they're sort of fixed in the composition that they have. And of course, then you get down here to the bottom, and it's all solid. So when we do real microstructures, they're not equilibrium, but they're chord, meaning that you've got a nickel-rich region in the middle and a copper-rich region in the outside. And that changes this from what we would get if we could do this really, really slowly. You'd have a lot of time for things to diffuse. But if you do this really slowly, you'd also have very large grains. So it's really cooling it slowly is not an effective way to really get out of this either. The effective way is you cool fast and you heat at some temperature where it's solid, high temperature in the solid solution region. And then what you can do is get solid state diffusion to equilibrate that composition. And equilibration exercises like this are very commonly done in industry. They call it homogenization. This is one of the first steps in making steel or aluminum. You cast it, then you'll often homogenize it, and then you'll roll it, and that can give you really good structures. So I'm not going to go into as much detail on this, not that I'm going into a whole lot of detail on anything, but the other system that we're really interested in is eutectics, and this is a binary. Binary means two component. Eutectic. Eutectic means you've got this lower melting region in the middle, and the eutectic point is defined by where you have this point here where you go from liquid, go just beneath it, you go from liquid to alpha plus beta, and this happens over really just a very discrete temperature here. And you notice this eutectic temperature is lower than either of these. So this is a trick that we very often use in making things like soldering alloys and brazing alloys, where we can make something that melts at a low temperature but has fairly high strength at ambient temperature. So here we've got three single phase regions. The single phase regions here are liquid, alpha, and beta. We've got limited solubility. You can see even at this eutectic temperature, if I consider how much silver I can put into copper, I can only put about 8% of silver into copper. So I've got limited solubility in alpha. I've got 8% solubility of silver and copper. If I go the other way, I've only got about 8.8% solubility of copper and silver. And then T sub E is this eutectic temperature. It's the lowest temperature. And then you've got this eutectic reaction, where the eutectic reaction is defined by this liquid. If you go just below the eutectic, it goes to alpha plus beta. So if we do what we've done before, we can do everything we've done with the phase diagram before. If I consider this particular phase composition point, this is about 40% tin. This is the lead tin system. So this is all lead here. This is all tin here. If I consider 40% tin in lead, here at this phase point, I've got a two-phase thing. The compositions of each phase is this would be my composition of alpha, this would be my composition of beta. So the composition of alpha is, about 10% tin in lead. Composition of beta will be something like 4% lead in tin, SN. And the relative amounts of each phase as well. If I do this, I can again do my lever rule. This would be the full length from here to here. Is this closer to the alpha side or the beta side? Or you can see it's closer to the alpha side. It's going to be more alpha than beta. So it would be this length here divided by, call this R. It would be R over R plus S, which is going to be on the order of about 60%. And so it's going to be about 40% beta in the end. So what's really interesting is we can get these very interesting microstructures that form this way. If I cool into this region that's really all alpha solid solubility, you might get you have a little region here that's two-phased, liquid plus alpha, all alpha, and it just cools down, gives you a nice single-phase microstructure like we talked about before. If I go through this region, it's a little bit, it's fairly similar, and again, you get all single-phase. Now when you get down to this temperature again, you get something interesting that happens, Now you've gone from here to a single phase region to a two-phase region, so you get little particles of beta that start coming out, and where those particles end up, whether they're on the grain boundaries, the intercrystalline boundaries, or in between, or fine dispersion, depends very sensitively on the kind of temperature, time, history that you use, and there's been a lot of work on engineering that. Where you really get interesting microstructures in the eutectic systems, where your composition is your eutectic composition. Cool down from here to here. You go right from this temperature here, where it's liquid, goes to alpha plus beta, and then you get these microstructures that look like this. They're lamellar. Lamellar means plate-like in Latin or something like that. And you can see the tin and lead partition out in front of it, give these remarkable microstructures that look like this. So go from that to that. Microstructures, again, are kind of interesting. So let's consider something that's a little bit more interesting, where you've got a composition that's in here. So again, you can cool down this thing sitting here at liquid. You form alpha first. Alpha would have this composition. Liquid would have that composition. Boom. You go down just above the eutectic temperature. Here, R and S are about the same length. It's about half liquid, half alpha. So you'd get something like this. The remaining liquid is going to go back and do exactly what we had here, form a structure like that. So you get down to this temperature, the remaining liquid, which is shown as green, turns into this lamellar or stripy phase. Stripy structure, it's not a phase. A phase is a constituent within that. So to be a little more formal about this over here, just above the eutectic temperature, what you've got is the composition of alpha is going to be about 18% tin. The composition of the liquid here is going to be about 61% tin. Tin is the same as SN. And then the weight fraction of each is going to be on the order of about 50-50. Be a little more precise, pretty darn similar in length there, R and S. And then just below the eutectic temperature, alpha is going to have this composition of about 18% tin. And the composition of beta is going to be about 3% lead, and then that's basically what you get. And the total weight fractions that you have for each of these, is this going to be more alpha or more beta? Composition points here. See, it's closer to alpha. It's going to be about 30% beta, 70% alpha when it's all said and done. And it's in this structure where some of the alpha is in these primary particles, and then some of it is in that eutectic lamellar phase, the eutectic lamellar structure, which is made of alpha and beta. So this is what real microstructures look like. If you cool through this area, we call hypoeutectic. It's less than the eutectic composition. You see alpha forming first, then the eutectic in between. Form at the eutectic, you get this stripy phase, stripy structure. Easy to call it a phase, it's not. And then you get down here to the hypereutectic, down this composition line, you end up forming beta first with this composition over here, and then you form the lamellar structure later. Okay? But I'm going quick, but it works very well. These phase diagrams come everywhere. And if you look at the iron-carbon system, there's two really important points. One, if you have the cast iron system, works on this eutectic, has a lower melting temperature, makes it easier to cast. This is what you see here. This is a eutectic in the iron-carbon system, much lower melting temperature than pure steel, pure iron. And then the other one that's really important is what we do in steels. We have something called the eutectoid, which is a lot like the eutectic, but the oid means this is all in the solid state. You go from this phase austenite, which is FCC, just beneath it. You end up going to what we call ferrite here. And this is a body-centered cubic phase. And you go just beneath this, and that wants to phase decompose into cementite, Fe3C, and ferrite. And again, you get this stripy lamellar phase, lamellar structure, which is called perlite. That perlite is made up of two phases. These dark stripes are iron carbide, Fe3C, and the gray area in there is basically alpha iron with BCC iron, and that's perlite. And this particular structure is what we call fully perlitic steel, and this is what we use in railroad rails. Railroad rails are very commonly made of fully perlitic steel. So now you understand how rail steels are made in that structure. It turns out it has very good wear properties, very good hardness. It's also fairly tough. It's all based on understanding phase diagrams. You can explain it by understanding phase diagrams. One more system I'll tell you about, and this is the aluminum gallium system. So what we end up getting here is kind of an interesting one. If you put aluminum and gallium at very different melting temperatures. So this is aluminum over here. This is gallium here. Gallium is a liquid around room temperature. You get here at about 270 degrees C, and just a little bit of gallium, and this is really eutectic here. And what you have here is aluminum plus liquid just above this temperature. And so if you have just a little temperature, you can end up with aluminum plus gallium there. And the gallium can be weak or liquid, and that can go along grain boundaries and embrittle it. And you've got just a small amount of, if you're over here, you can have just a small amount of gallium that's present, and possibly in the liquid phase it tends to segregate along the grain boundaries, and it's a way you can actually cause aluminum to fail along the grain boundaries. Each of these are grains, they're crystals, and this can be a bad thing. This is called liquid metal embrittlement. But it's also kind of a cool thing in that it opens up a structure and allows you to see how those crystals pack together. So these are all individual crystals, kind of harkening back to what the material structure looks like. And again, you can explain that this small amount phase segregates, a little bit of gallium wants to still be liquid, finds its morphology on the phase on the grain boundaries. It can be an embrittler. And there's some neat U-tubes on what aluminum will do to gallium. It has been used, we think, for nefarious purposes in the past. So I'm going to end here. Summary: phase diagrams are a useful tool. It can tell you three basic things: number and types of each phase, the weight fraction of each phase, how much of each is there, and what the composition of each phase is. What you got to know is temperature and composition. And this has to be an equilibrium. We know how to deal with things that aren't as well. And the other important point is this is right now for a two-phase system. We can also do this for multiple phase systems with higher order phase diagrams. We can also produce solid solutions. These can increase the strength. Eutectics and eutectoids allow for a wide variety of microstructures. And then we, for real, use thermal mechanical processes, but we're going to leave this for another day. I just want to end on an acknowledgement. These are slides I'm using that were developed for our service course that used to be called 205 and now 2010. And Pete Anderson on our faculty is the guy that put this series together, and it's a nice one, and I'm kind of doing it at turbo speed. Happy to answer more questions on the website. We will also put links to other resources if you want to go more deeply into this. And that's basically it. Thanks, and see you again soon.